Hello, my name is James Callan, and today I'm here to present my work, Multi-Objective Genetic Improvement, a case study with EvoSuite. I produced this work in collaboration with my PhD supervisor, Dr. Justina Petka, and we're both based at the University College London in the United Kingdom. This paper was submitted to the challenge track at SSBSE 2022, in particular to the contest for improving an existing search-based software engineering tool, EvoSuite, using a search-based software engineering technique. So first of all, what is EvoSuite? EvoSuite is a search-based software engineering tool which is used to generate tests for Java programs. EvoSuite uses evolutionary algorithms like genetic programming to generate new tests for particular classes in a Java program with the aim of achieving high coverage. EvoSuite starts with randomly generated tests and iteratively improves them to cover more and more of the class of interest until hopefully the entire class is covered. EvoSuite is split into different modules which are responsible for different things. There are a number of side modules for things like plugins and creating a runtime jar. However, the two main modules that we're interested in are the master module and the client module. The master module is responsible for parsing the user's command line input and creating an environment in which test generation can happen safely. To do this, the master creates a sandbox. The sandbox allows tests to be generated freely and without any risk to the environment around them. The master creates this sandbox and within it spawns the client process, which is responsible for the actual test generation. In general, EvoSuite gives the client process a set time limit to find tests. Therefore, any performance regressions will reduce the amount of test cases that it can evaluate and thus the coverage that it can achieve. We hope that we can improve the performance of the client module, thus allowing EvoSuite to generate more tests, execute more test cases, and ultimately produce better results. We plan to improve EvoSuite by making changes to its source code. In order to make sure that these changes were safe and valid, we plan to use EvoSuite's test suite. Investigating EvoSuite's test suite uncovered the fact that it was very thorough, achieving almost 100% coverage in both branches and lines. This gave us confidence that we could safely modify the source code of EvoSuite to confirm whether our changes were valid or not. Given EvoSuite's thorough test suite, we were able to use the genetic improvement approach to attempt to improve the amount of test cases which EvoSuite can process. Genetic improvement is a search-based software engineering technique which attempts to find patches which can somehow improve a program with respect to some property whilst maintaining its functionality. Genetic improvement uses heuristics or meta-heuristics to search through a landscape of potential patches in order to iteratively find better and better patches with respect to the property being improved. On the left we can see a representation of a patch within the GI framework GIN. This patch is made up of two edit statements. The first edit is a copy statement edit, and this edit takes a statement from one part of a program and copies it to another. Next we have a delete statement. This simply deletes a statement from within the program. And the other statement level edits available within GIN are the move statement edit, which moves a statement from one part of the program to another, and the replace statement edit, which replaces one statement with another statement. We can then see these edits applied to the actual program. We see that the delete statement simply removes this recursive copy method call, and the copy statement inserts a while loop at the bottom of the method. This isn't a particularly good patch. Firstly, removing the recursive copy call on its own would remove the functionality of this particular function and cause it not to work properly. And inserting this while loop here would not only be useless as it would simply waste time, it would in fact not compile, as the string and in variables have not been assigned before they're referenced here. GIN produces many statements like this. However, it discards them and over time iteratively aims to find better and better patches, and actually eventually find patches which not only compile and preserve the functionality of the program, but also improve it with respect to some property. Once we have a patch that's been produced by genetic improvement, we have to validate it in order to ensure that it doesn't somehow change the functionality of the program or introduce new bugs. In order to do this, we use the test suite of the program, in particular the test cases which cover the area of the code which we wish to improve. In the case where all of these test cases pass, we say that the patch is valid and will continue as a part of our population. However, if some or all of these test cases fail, we say that the patch is invalid and we throw it away. During this test case execution, we can also measure either the fitness or the fitnesses of the properties which we are wishing to improve. For example, if we're trying to improve the execution time of a program, we can simply measure the time taken by the test cases which we execute and use this as our fitness. This means that if we can find some patch to the program which will make it faster, the test cases will execute faster and thus the fitness will reduce. So we can use algorithms to search for a landscape of patches to increasingly smaller and smaller execution times until we have a much more optimal version of the program. As we want to allow EvoSuite to generate and execute more test cases, we want to improve the execution time of its client module. However, this can have negative impacts on its other properties. If the execution time of a program is improved, this can often come at the cost of the memory usage of the program. And if the memory program gets sufficiently big on a small device, this can result in excess garbage collection calls and pauses and ultimately have a negative impact on the execution time. We can see an example of how improving the execution time can actually negatively affect the memory consumption of a program. This is a simple example consisting merely of the instantiation of a new array list of integers. In the first example on the left, we instantiate this array list with a capacity for 10,000 integers. This means that we can add up to 10,000 integers without having to worry about the capacity of the list having to be changed by the Java virtual machine, and thus taking more time. However, this consumes excess memory which may not be necessary if the list is only ever full with a small amount of items. On the right we have a more memory efficient implementation with capacity for only 10 integers. However, if this capacity is reached and more integers are attempted to be added, costly new operations will be needed to assign more memory to this array list, thus making it less optimal for the execution time. Because of this, we want to take a multi-objective approach to our improvement, allowing us to safely improve the execution time of EvoSuite without having to worry about any negative impacts that we might have on the memory consumption. We may also be able to find more memory consumption optimal versions of EvoSuite, which could be useful for smaller devices with lower memory capacities. Here we can see an overview of the whole process of genetic improvement. In genetic improvement, we begin with the source code of the application which we wish to improve. We then apply an iterative process to a population of patches on that source code, with the goal of finding a population of patches which improve the source code. At each step of the process, we begin with a population of patches. Firstly, we use the mutation and crossover operators to modify and recombine the patches. This will produce a population of new patches, and hopefully some members of this population will be an improvement upon the best members of the previous generation of patches. However, in order to find this out, we must test the patches. To do this, we first apply the patches to the code, giving us the patch code, which we then try to compile, and then we can run our tests. If the patch cannot be applied, or if the code can't compile, then we discard the patch. We then test the patch, and at this stage we can also measure the fitness of the patch. So for example, if we were trying to improve the execution time of the program, we could measure the time taken by the test case on the patched code. If all the tests pass, we can keep the patch and move on to the selection phase. In the selection phase, we attempt to choose the best members of the population, however also maintain diversity. In a single objective setting, this is fairly simple, and patches can be simply chosen based on having higher fitnesses than other patches. However, in the multi-objective setting, there may be trade-offs to be found between different properties. So any selection operator that is used must be able to determine whether one patch is better than another, even if they may be better in one respect but not as good in another. The particular operators used will be determined by the meta-heuristic selected. So for example, genetic programming can be used, and then for the selection operator we could use either tournament selection and put patches up against each other, selecting the best one, or roulette wheel selection, selecting the patches probabilistically based on how good their fitness is. For our experiments improving the execution time and memory usage of EvoSuite, we had to select a mutation operator. For this, we chose the NSGA2 algorithm. This algorithm has been successfully used alongside genetic improvement to improve memory usage and execution time in the past. NSGA2 is a similar algorithm to genetic programming. It uses crossover and mutation operators to recombine and modify patches. However, as this is a multi-objective setting, we need a different selection operator that can find good trade-offs between different properties. The selection operator used in NSGA2 has two phases, one in which the patches are sorted in Pareto fronts. This means that those patches which are ranked higher find better trade-offs than those in lower patches, and then a crowding operator, which attempts to select those patches which are more diverse in terms of their fitness. In order to improve EvoSuite using genetic improvement, we needed an implementation of it. We chose to use the Genetic Improvement in No Time framework, also known as GIN. GIN has all of the tools needed to improve Java programs using genetic improvement, including implementations of different edit types, the ability to apply the edit types to programs, compile the programs in memory, and run tests on the compiled versions of programs, along with the ability to measure both the execution time and the memory usage of the program being improved. However, GIN does not include an implementation of the NSGA2 algorithm, or at least it didn't when we started our experiments. So we created an implementation of NSGA2, which has now been merged into the main branch of GIN. This makes our work incredibly easy to reproduce, as you merely need to download the main version of GIN and follow the instructions in the README. It also is the first open source implementation of a multi-objective algorithm within a GI framework. So people are now free to use GI for multi-objective frameworks in the future. The other main framework that is available is the Piggy framework. This is a language agnostic framework, and in order to run it on Java programs, significant work would be needed to implement some missing features to run specifically on Java programs. Thus we selected the GIN framework for our experiments. In order to run genetic improvement on EvoSuite, we must select the methods that we wish to improve. Ideally, we would improve the methods which are responsible for the worst execution time and the most memory usage. To find these methods, we use the built-in profilers from GIN. We simply pass the project to GIN and it runs the tests and determines which of the methods are most responsible for poor execution time and the most memory consumption. The profiler also has the benefit of finding all of the tests which cover the methods which it finds responsible for poor performance. We can then simply pass these methods and tests to the main GIN framework, which can then run genetic improvement and optimize all of the methods that we pass it with respect to both execution time and memory. So here we have the methods that we selected. The profilers actually put out more methods than are present here, however we excluded some of them. We excluded those methods which had less than 5 lines of code, and only kept those with more than 5 lines of code, as these methods did not have enough room for modifications which might actually improve them. These methods were likely calling other methods elsewhere which were actually responsible for performance regressions. We also only selected the methods which had associated tests which all pass when run using the GIN test runner. Some of these methods passed when run regularly with JUnit. However, due to a bug, either with an improper configuration or something in the GIN test runner, certain tests might fail, so we excluded any methods with these associated tests. This left us with our set of methods, which we ran GI on each of them and present results for all of the methods in the following slides. So here are the results from our experiments. For our experiments, we ran genetic improvement using the NSGA2 algorithm on EvoSuite 10 times. We ran it 10 times in order to get a better understanding of how genetic improvement performs more generally on EvoSuite. In this particular table we present statistics about the patches we found which improved execution time the most across our experiments. In the first column we see the method being improved. In the next we see the median improvement to execution time found by the best patch in each of the experiments, then the maximum improvement, along with the impact that the best patch we found for execution time had on memory. And then finally we show the line coverage achieved by the tests on the methods that we improved. We can see that the line coverage is very high in all of these cases, so we can be confident that the changes we found didn't break anything and were valid. The median improvement and the maximum improvement found across most of the methods were surprisingly high, in some cases up to almost 80%. We found that our best patches, however, did have small negative impacts on the memory usage, increasing the memory consumption of the program. However, in most cases, when compared to the execution time gains, these small detriments to memory use do seem worth it, and would only be relevant on devices with very small memory usage. I would also like to draw attention to the best patch that we found, which achieved an almost 80% improvement to execution time. This patch achieved this improvement by simply removing a method call to get the canonical name of a class with regards to a particular class loader. This method was wrapped in a try-catch statement in which an exception could be caught, however was immediately discarded and the program continued to run as is usual. It was also accompanied by a comment which stated that this part of the program would only be relevant in certain testing scenarios, and that in regular use of EvoSuite, the class loader should be configured correctly and thus this method would not be needed to be called. This means that we believe that we can safely remove it for general usage of EvoSuite. However, more consideration would be needed about whether this improvement was worth it in general for the impact that it may have in certain testing scenarios. Next, we present similar results, however, for the memory consumption of the patches. Again, we present the median improvement across the 10 runs and the maximum improvement found. We also present the impact that these patches had on the execution time. We can see that the memory usage increases were significantly smaller than execution time. However, still some reasonable improvements were found. We found improvements for all of the methods except for one, and in many cases we found improvements which improved both the memory usage and the execution time without having to trade off between them. The best improvement we found reduced the memory consumption of a method by 9.2%. This particular patch had a few changes, however the main one seemed to be the changing of scope of a try-catch statement, moving some code out of it, thus freeing up the resources associated with a try-catch statement. We also wish to see what impact these patches can have on the actual test generation of EvoSuite, as this was the main aim of our experiments. In order to do this, we took our most impactful patch, the patch which achieved an almost 80% improvement to the execution time of a method, and compared it to an unpatched version of EvoSuite. We ran both the patched and unpatched versions of EvoSuite on the example project from the EvoSuite website. We repeated this process 20 times with a set time limit, and saw how many test cases EvoSuite was able to execute during this time. We found that the patched version of EvoSuite was able to execute 5% more test cases than the unpatched, thus exploring a wider part of the landscape. If we were to apply the patched version to large programs with more trouble finding coverage than this small simple program, we would expect our version of EvoSuite to perform better, exploring more of the search landscape, evaluating more potential tests, and ultimately achieving more coverage. In conclusion, we found that genetic improvement is capable of improving both the execution time and the memory usage of EvoSuite. In some cases, GI is capable of finding trade-offs between execution time and memory, and in others finding patches which improve both of them at the same time. We also find that when running these patches, applying these patches to EvoSuite and running the improved version, EvoSuite is capable of generating and testing 5% more test cases than without our changes, and is thus able to explore more of the search landscape and hopefully achieve higher coverage. We also provide the first open source implementation of a multi-objective algorithm for genetic improvement. The implementation of NSGA2 is now available through the GIN Genetic Improvement in No Time framework for anyone to use, whether they want to apply it to their own programs to improve their memory usage and their execution time, or whether they want to reproduce the work from this paper.